Alright, so full screen, that's what I want. Alright, so example 1. An open top box is to be made cutting congruent squares of side length x from the corners of a 20 by 25 sheet of metal and bending the sides. We did this a lot in pre-calculus, actually. Optimized for maximum volume. Okay, so let's draw the sheet and the box first of all. So I have a rectangular sheet of metal. And then I'm going to cut out of these corners. Congruent just means the same. Squares with length and width of x. Okay, and so if you cut these out and folded along these lines that I'm drawing now, these corners would come together and you would have this open metal box. That's where that comes from. Okay. So I said maximize volume here because I need to have a volume equation, okay, for this box. So can somebody give me a volume equation for the box?
X times parentheses 20 minus x.
Good. The height of the box once you fold up the corners is going to be x. This was 25, but I cut x off each side, so that now would have a width or length, whatever we want to think of that, as 25 minus 2x. And what would the last one be? 20 minus 2x. Okay. I'll try as best I can to give you guidance on your homework, which would be non-calculator and which would be calculator. On this one, what I found was I can multiply this out without my calculator, but when I actually do critical values, they're not really that nice, so we are going to have to use our calculator using quadratic formula to find them. So let's multiply these together first, okay? I'm going to multiply and then multiply everything by x. What's 25 times 20? Oh, come on, guys. 500. Minus 50x, are you following this? Minus 40x. Wouldn't that be minus 90x?
Yep.
And what's negative 2x times negative 2x? Plus 4x squared. Multiply everything through by x. My volume equation then, and I'm going to rearrange the order because I like to have the highest power first, would be 4x cubed minus 90x squared plus 500x. Okay. And I want to maximize this. Okay. Now, how would we do this in pre-calculus last year? We would have graphed the volume and we would have looked for a maximum. How do we use what we now know in calculus to do that? Take the derivative, find the critical numbers, and find which one is the maximum. Okay? So, I am going to now take the derivative. And what do I get? 12x squared minus 180x plus 500. Okay. Now, I am going to find the critical numbers, so I'm going to set this equal to 0. And my options now would be factoring if it was nice, but I already told you it wasn't nice, or quadratic formula, okay, if it's not nice, which I already told you it's not. So let's do quad formula. Some of you might still have a program, but we'll set it up anyways, just in case you need to know. X equals negative b, which would be positive 180, correct? Plus or minus square root. B squared, which would be negative 180 squared. I wrote it this way because I know that negative 180 squared, when it's squared, becomes positive, right? Okay, what comes next? Minus 4 times 12 times 500 all over 2 times 12. Okay, let's do this.
It'd be 4 times negative 500.
What?
It'd be 4 times 2 times negative 500.
Ooh, that makes a big difference. Why is it negative 500?
Yeah. No way, negative numbers.
What?
It's positive. Get whoop. Minus Jolly Rancher. Since I'm not a teacher, so
Alright, here we go. I am going to do this 180 squared minus oh, I don't want to do that. Minus 4 times 12 times 500. Now I'm going to close the parentheses. Alright. Do you see how I got 91.651? I'm going to keep it in there. Right? Okay. So I have 180 plus that answer divided by 24. X is approximately 11.319. Oh, well, let me go back up to that. Mine won't. Second entry. Second entry. Second entry again. Oh, look at that. Okay. It's a little things in life that bite me. Alright. Divided by 12, and is that right? Oh, crapola. Yep. Okay. I knew that wasn't right. Alright, now, this is the word problem. So here's what we're deciding. We know that this is continuous. It's not a closed interval or anything like that. So my potential maximums are this. We're going to use second derivative tests to see which one's the minimum or maximum, or vice versa. But I'm going to throw one of my answers out. Why? What happens if I put 11.3119 up here into this, where my pencil is? You get a negative dimension of the box. Okay. I'm going to cross that sucker right out. Alright, so this is my critical value. Why? Because it is where the derivative is 0. To confirm that it's a maximum, in my head I know it must be, but to confirm it's a maximum, I'm going to use the what test? Second derivative test. And all I'm looking for is a positive or negative number. If it's if the second derivative is negative, that means it's concave down, negative concave down, but if it's concave down, that looks like this. So there's a maximum. Okay. So let's go. Double derivative. We get 24x minus 180, correct? Okay. The double derivative of 3.681 would be 24 times 3.681. Well, since I'm using my calculator, I might as well do that anyways. Times 3. Okay. Minus 180, it's clearly a negative number, correct? Okay. So that means v of x is concave down when x equals 3.681. Therefore, you don't have to write out the word therefore, you can use the 3 dots. I showed you that in pre-calculus, right? Therefore, 3 dots, or write out the word therefore if you don't like that. This is where a maximum occurs. Okay, let's just make sure that we answered the question. Did it ask a question? Optimize for maximum volume. Let's write out the dimensions, okay? The dimensions would be 3.681 inches by, what do I have to do?
25.
What's 25 minus 2 of those?
17.638.
I'm going to just do this instead of the little quotation marks. By, and then what was
12.638.
12.638 inches would be the dimension of the box. Okay. How we doing?
So the maximum volume, do we want to know that?
We should. How would I find the maximum volume of the box then?
Multiply them together.
Yep. And let's make sure we realize that these are approximate. Max volume is approximately 820.528 inches cubed.